Today's guests are building something absolutely wild, a cheap fabrication machine powered by a particle accelerator shrunk to a very, very smaller size that's never been done before. So we have Rohan and Daniel, the founders of Inversion Semiconductors, and they're aiming to make the world's most powerful chips 15 times faster than anything out there. We see you, ASML. So if it works, it won't be just a tech breakthrough, it could reshape the global chip manufacturing and bring advanced chips back to the US. Let's get into it. Guys, I'm so excited to have you here. How are you?
Yep, thank you, Gabriel. Very nice to be here today. Thanks for taking the time to have us on.
Awesome. Let's get into it. So please just, introduce yourselves. Who are you guys? What's Inversion? What are you trying to accomplish? Maybe I completely messed it up. I think I was probably, hopefully close, but I'd love to hear it from your own words. Who are you guys and what are you building? Because it's so exciting.
I think you hit the nail on the head with the summary. We're Inversion Semiconductor. I'm Rohan. I'm with Daniel, my co-founder. And what we're doing is we're on a quest to build the next generation of machines that will manufacture the most powerful chips that have ever existed and do that here in the US, building the US ASML. And that is a huge part of the mission. How can we reshore this capability, which has really been offshored to other parts of the world, primarily Asia, and how can we bring that back over here to the West? And the way we're doing this is we're leveraging this incredible technology of the compact particle accelerator. And we can go into the details of how all of that works. But at a very high level, it turns out that using particle accelerator technology really gives you these inherent advantages when it comes to manufacturing chips. And so we can use this to build a lithography machine. Lithography uses light to expose circuit features onto silicon, kind of analogous to film photography. Instead of exposing a photograph, we're exposing circuits onto silicon. And with that light, we're able to do this at very high volumes. Optical lithography, what I've just described, is actually the only method we have for manufacturing chips at extremely high volumes today.
All right, Rohan, that's amazing. Daniel, I want to turn this to you. I'll ask you a simple question that I'm guessing most of the audience is asking itself right now. It's like, okay, those guys want to kill ASML. Why wouldn't ASML just do it? They're a $270 billion company. So why are you going to be better than them?
Yeah, we've gotten this question a lot, through this entire process. And actually, ASML took a look at using particle accelerators way back when, especially with the Jefferson Lab. They showed really good work on making these systems work. But even back then, the big problem was that these systems end up being very, very large. And there's only a couple of companies or even countries around the world that are willing to build massive particle accelerators in their backyard just specifically for chip manufacturing. So back then it was not that feasible. ASML, instead went towards LPP or laser produced plasma, which is what, is the process today. It was cheaper. It seemed a little bit easier to do. And then, its whole thing. But now we feel like we're in a place where a lot of the technology that made these particle accelerators massive has become a whole lot more advanced, a whole lot cheaper, so we'd be able to do it. In addition, ASML, what they are first and foremost is a master integrator. They've designed, their lithography machine, but at the end of the day, they're not the ones making the mirrors, they're not the ones making the motors. They have to rely on a huge supply chain to bring all these parts together to make one lithography machine. Um, if they were going to build a new particle accelerator to produce light for a new lithography machine, that whole supply chain would have to change radically than what it is today to be able to accommodate for that. Um, and that's a bit complicated. Even if you're a very large company like ASML, you'd have to rethink your supply chains. You'd have to rethink everything about the machine, um, and especially the semiconductor industry is something that is very conservative. It wouldn't be a very good look for ASML to go something so radical. Um, we are in a great position to take on that risk and be as radical as we can be, because if it pays off, we are going after ASML.
That's the sort of the eternal thing, right? Big company can't move, can't innovate, too risky, too slow. Small incumbents comes in and then change the world. Okay, so get us back, whoever wants to take this to sort of the beginning. What's the spark or the light bulb moment where you're saying, okay, let's actually build a photolithography machines that it's so complex, there's only one company in the world doing it, we're actually going to do that as well?
So I think some context, a bit of history about my background and Daniel's background will help to put this
Yeah.
Please.
into context. So just before building Inversion, I was at Arm. So for anyone who doesn't know, Arm is a chip design company. They license out designs to every other chip design company you can think of, from Apple to Broadcom, Qualcomm, and they've got a really interesting business model because they license out their IP, but they sit very firmly in the design side of the industry. So the semiconductor industry is broadly split into the design side and the manufacturing side. And those are pretty separate in most cases. Uh, so at ARM, what I was doing was automating chip design in the systems group, and that was great experience, turning subsystems into products that get sold to ARM's customers. But what I really had the chance to appreciate while I was there was that a lot of the innovation in the semis industry is driven by the manufacturing side. And all these companies we look to who manufacture and design these wonderful chips, NVIDIA, Apple, AMD, they are playing within a set of constraints which is set by the fabs, TSMC, Intel, Samsung, a couple of emerging fabs as well. And in turn, what drives their capabilities is the supply chain of tooling and equipment that they use. And there happens to be this single point of failure in the industry today, which is with advanced lithography, with ASML being the only company in the world that makes these machines. And so that was a little bit about my background coming into this, meeting Daniel, and I'll let Daniel say a little bit about his background.
Yeah, so my background, grew up in Southern California, went to school down over at UC Irvine, where I worked on numerous projects, but the most relevant to what we're doing today was working for a company who was building compact particle accelerators for cancer treatment. These were still your traditional particle accelerators, but what they were doing very well, um, they were able to accelerate electrons to very high energies, produce X-rays with them, be able to take a picture of someone's chest, for example, find tumors in the lungs, and focus in electrons for radiation therapy. Back then, what this machine was able to do was produce a whole bunch of X-rays using laser Compton scattering, uh, which sounded amazing. And then, the immediate thought there was like, huh, I wonder if this could be applied to other areas, like lithography, for example. But the architecture for that machine didn't quite work for what was needed for lithography, the high stringent requirements. And it came down to, well, if we wanted to make a machine to be able to meet those stringent requirements, we'd end up with a very big machine. Same problem that ASML had when they took a look at this. So that went on the back burner. Then I went to grad school over at University College London, which where Rohan and I met was in London. And part of the work there and part of the research I did there was exploring these new class of advanced particle accelerators that use plasma to accelerate electrons to very high speeds. And with that innovation being done at CERN, all over the UK and Europe as well, it became, potentially feasible that this could be possible now, that you could build particle accelerators to power a lithography source. And that's, that was the inception of it. This, at least on my end, that great knowledge of the work that was being done in academia in terms of particle accelerator physics, being able to work at CERN and see their advanced plasma accelerator as well, and understand how is this going on, and then Rohan's experience working at ARM to see like if you're a chip designer, what matters to you most, because at the end of the day you are the one that's using the company or the tool. Apple designs their circuit, and it gives it over to TSMC, but that circuit is very dependent on what TSMC can do. And that really starts at the lithography step. And we're trying to free that up as much as possible so someone like Apple, other designers can come in and really let their imaginations go wild and produce things that are just not possible today.
That's pretty awesome description and background. And when you realize, what was the first moment when you realized, so okay, plasma can actually accelerate particles fast enough to make this new generation did you already know about lithography machines, or were you sort of fishing out there, hey, what can we use this for? And then when did you guys decided to say, okay, let's do it, let's try to build this?
Yeah, at least for me, I knew about lithography, at the very surface level that, like Rohan mentioned, it was light used to produce chips, but I didn't know much else back then. I was like, oh, this is a really cool application. If we can find a way to use particle accelerators for this application, it'd be very cool. Then, during my research, got experience using these plasma accelerators. And, on my end, I was like, okay, time to learn a whole lot more about what lithography actually is, what sort of requirements we need to be able to build a light source capable of producing lithography.
And from my
Right.
perspective, I had no idea about compact laser Wakefield accelerators until I met Daniel. But what I did know, I'd built this great context of the semis industry and where these single points of failure are. And almost in the back of my mind was just thinking about what could be a compelling competitive technology to what ASML is building today. Does such a thing exist? Where could I find it? And it really organically just fell into place when I met Daniel. You had these two pieces of the puzzle with semis and particle accelerator physics. And in a way, these compact laser Wakefield accelerators are approaching this point of inflection that large scale accelerators have had in the past. Large scale accelerators, they aren't just kept in the research lab. They're used in industry for a number of applications, whether that's cancer therapy, whether it's food pasteurization, radiation testing, non-destructive testing in industry. So I feel like the compact form factor accelerator is fast approaching that point of inflection. And while we are one of the first companies in the world to look at applying these to a very exciting use case of lithography, give it a couple of years and other players will pop up really focused around other applications.
Can you name some
Some other applications, yeah, absolutely. So
yeah
we've even looked into this ourselves, spent a long time thinking about how else these compact accelerators could be used. But for us, some of the most exciting are applications for the new space industry. So, a lot of companies are emerging and are having to do a lot of testing of parts, whether that's non-destructive testing, radiography, so using high energy X-rays to be able to look into a part and understand what kind of failure modes might be going on, fractures, cracks, etc. And then the other one is radiation effects testing. So think this is something that pretty much every single satellite company has to do. When they send any electronics to space, they've got to make sure that these electronics will survive the radiation environment in space. And so the way they do this is with a couple different types of radiation testing. One of those is just seeing under continuous exposure to radiation, how long will my electronic assembly last? Another kind of radiation effects testing is single event effects testing. So rather than a continuous stress test, single event effects is really testing for unique cases where you deliver a high burst of radiation energy to a chip and you want to see what kind of failure occurs. Do you get a latch up, a burnout, something else? And that's something that happens frequently when you're in, especially geosynchronous orbit and beyond, and is very important to test for because it informs what is the reasonable lifetime of this mission. Can we expect this satellite to be in orbit and operating for 70 years, 100 years? And this kind of testing gives you that information.
That's very cool. Lots of application, and I'm a big believer in the new space. I've invested in some of them. I've hosted some in this show, so I'll put you in touch for those who don't know you already, if they need to test. Can
Nice.
Absolutely.
it is, yeah, sure. It is a, I don't know. To me, it seems like an obvious, company that should exist. An obvious bet. You guys are going to try this very hard thing and hopefully succeed. I want to say very likely, but let's say we don't know. Maybe you won't. Maybe you will. I'm wishing you all the luck, obviously. But was there a, and I think everyone realizes that. I remember, at YC during your demo day, I speak to a lot of investors and everyone was like, okay, yeah, this is very cool. This is, obviously something very interesting. But was there a time much earlier where almost no one believed in you, sorry? Did you think of quitting? Did you think that's not going to work? And then who was sort of the first proof or the first investor or the first thing that made you say, okay, we're on to something really?
So, some good background here is Daniel and I, we met doing this incubator in London called Entrepreneurs First. It's got a pretty unique model compared to a lot of other accelerators where, usually the case is you've got a founding team, you've got some kind of idea, you maybe even started building, and then you get accelerated. Entrepreneur First is a lot more like an incubator. So they curate these cohorts of founders that they think could go on to build extraordinary companies. Maybe these founders have a bunch of ideas already, maybe not. And the hope is you find, you find your co-founder in the cohort, and if all works out, you go on to build a multi-$100 billion company. And so for myself and Daniel, it was, call it love at first sight. As we mentioned, really organically, the pieces of the puzzle for what we wanted to build had fallen into place. And it became very obvious to us that building a company together would be the most ambitious version of anything else we could think about building. But interestingly, while we started and ultimately came back to the concept of building an advanced lithography machine, there was a time where we'd explored a different idea higher up in terms of abstraction in the semis industry. So we were looking at uh, should we set up rapid prototyping foundries like what TSMC builds, but smaller scale and targeted at emerging architectures of chips like quantum compute, photonics compute, reversible compute. These are all, you might hear these terms being thrown around, very exotic. A lot of these architectures have had cycles where they've gained hype and then it's not really amounted to much. But I think we're at a point now where, especially for photonics and quantum, these architectures are now being commercialized. Companies like NVIDIA are building products around these architectures. And so we saw that what's missing is the ability to manufacture these kinds of chips at high volume and do this very quickly, go from an initial idea to a product as quickly as you can with traditional electronics chips. And so we spent a number of weeks looking into this, and we spoke to every single chip design company in these areas. We even got to the point where we were close to buying a fab and repurposing it to do rapid
Wow.
prototyping. And then ultimately, what we realized in talking to these companies is that if we actually go back to our original idea of building a new kind of lithography machine, we can address a lot of the problems that these companies have because current technology, current machines, current tooling can't be used to effectively manufacture these kinds of chips. You're looking at increasingly more three-dimensional features on the silicon, even bringing in novel kinds of materials. And we see that with the kind of lithography machine that we're building, some of the unlocks that we're going after in terms of the power and the wavelength of the light also enable these emerging architectures to be physically fabricated in ways that hasn't been possible before.
Yeah, and to add on to that, on the believability of this whole, endeavor, this was pretty much the first idea that we had. The second idea was the fabs that Rohan had mentioned, but we just reverted back. Never in our time together have we really ventured out and done something different, even against the pleadings of our advisors at Entrepreneur First, at our friends, and even our investors at times, because we sat down and thought about it for a couple of days. Like maybe we should do something easier, maybe something around AI or something around medical, which Rowan has a background in, but none of them sounded as exciting or as cool as what we were building. And since then, people have told us, yeah, this is not possible. It's too hard. It's this, it's that, and the other. But at the same time, a lot of people have supported us and told us, that's very cool. I don't know if it's going to work, but, give it a shot. And at least, for us, what we're building and this whole idea is something that is very unconventional. Not many people believe in it. Only a really small handful of people have real strong conviction. And at least for me, that is a place where I want to be, because it's always, impossible to do until it's done. And then everyone's going to be like, it was there all along. We could have done it if we all tried. But at the end of the day, we'd rather work at the edge of what's possible and impossible. Because if it turns out, it's too hard and we can't do it, we're young enough to go and try another impossible thing. And if we make it work, then, well.
But in both cases, you win, because if you make it, that's great. If you don't, you learn so much. Maybe on the way, you uncover something else. So I completely agree. Okay, I wanted to point out something interesting for me, because I'm from Europe. I'm from Paris. Uh, uh, Daniel, you're from California, but Rohan, I don't know if you're from the UK, but at least you were based in the UK, and
Yes,
you're
I
from there
grew
as
up in
well,
the
right?
UK.
Yeah.
Yeah.
Exactly, right. And then you guys met in the UK, you did the incubator in the UK, and then you decided to come and build this here in San Francisco, or in the US. Um, being from Europe, I have some investors in my fund that are from Europe, French, and all over the continent. And it's this thing we hear all the time. Is Europe catching up to the US? I personally think, sadly, Europe is dozens of years lagging behind and far from catching up. Why did you choose that? Why not build in London? Why not build in Switzerland next to CERN? Wherever. What motivated your choice? And again, I think it's a great choice, but just to sort of double down on that concept.
I think the reasoning is there's many levels to it. Right from the beginning of building this company, something that we realized very quickly is how different the mentality of people in general is in Europe compared to in the US. And so, I love the UK. I lived in London for basically 5 years before coming over to the US, miss it dearly as a place to live. But when we were building the company in the early days and we would reach out to people for advice in a tech, from a tech point of view, a lot of the time we were told all the reasons why we shouldn't build this company and why it won't work. We are young, relatively inexperienced compared to people who have spent their whole careers in this industry, and you have the battle scars to show, and they really do show when you speak to them. Meanwhile, when we came over to the US and started speaking to people in the same capacity, looking to validate parts of the tech, getting advice in these domains, it really changed that mindset. And it became a question of, I don't know if you guys are going to pull this off or not, but I don't care. It's not my problem, it's yours. So I'll tell you what I know. I'll answer all your questions to the best of my ability, and you can do what you will with that information. But just that shift in mindset and being surrounded by that mindset really does feel like it makes a difference on a day-to-day basis. And then, a lot more tangible reason for building the company in the US, uh, especially in the short term, is that for Daniel and myself, a huge priority was from the beginning, how do we access the best talent in the world uh, in order to build this technology? It just so happens that the world's leading research group developing these compact particle accelerators is Lawrence Berkeley National Lab, particularly the Bella Center over there. And they are one of our key technical partners. We really prioritize building the relationship with them early on. And so not only are we based in the US, we'll be based in Berkeley itself, so we can be close to them. That really just makes a lot of sense.
Yeah.
It's
And if I
awesome.
were to
And
add on,
oh, sorry, go ahead.
yeah. For me, I would say the talent in Europe is on par what you see here in the United States. There are pockets where the talent is just out of this world. Even over at UCL, their CS department is one of the best in the world. Imperial is one of the best in the world. Oxford, Cambridge, you have ETH, EPFL, École Polytechnique, TUM, great institutions all around, and people who I've met in London and in Europe that have just blown me away a whole lot more than sometimes here in the US. And for me, a lot of the reasons why I think things just don't get done is because people are told don't do that, or go do something else, go do something easier, go do something that's a lot more sensible. And it's not, from the perspective of the young people who have all these great ideas, who want to try out all these great things. It comes down to, well, European investors take a month and a half to give you $100,000, and we've gotten $100,000 off the back of one call. Even in Switzerland, more on the more, banking and entrepreneurial side, and you still have to go through a massive checklist to make sure everything's okay before you even have a conversation of, how much are you looking to raise? The access to capital in Europe is a whole lot less because I think the risk tolerance is a whole lot low. Here in the Valley, what's great about it is that, like Rohan is saying, people are willing to talk to you, people are willing to give you a shot because they like you, what they think you're building is cool, and they want to help and want to see it thrive. And there's not much more thesis behind investing other than just vibes. If you vibe with the investor and what you're saying sounds okay, especially at the seed stage, they'll be like, yeah, why not? Let's see where this goes. Whilst in Europe, a lot of the issues we were seeing is that people wanted to have every little thing thought and proved out. And it's just really hard to do that if you're at the seed stage and no money. That's what you raise a seed for, to prove all those things out and then go on to build a bigger and bigger company. So if I had to change something about, Europe and building in Europe, is just people having a lot more conviction than that. Stranger things have happened, and a lot of these ideas, while crazy as they sound, one of them could work out. And we should be, betting a whole lot more on our youth and being really trusting of our youth that they are sound people, that they know what they're doing, that they do have this conviction to go out and build this, rather than veterans who are from an era that's gone past, that is not today.
I was listening to you. It reminds me of an example that absolutely everybody knows. It's when Elon Musk said, I'm going to land rockets. And everyone said, it's impossible. You can't land rockets. Everybody tried. It's just not possible. And lo and behold, look what happened. And, hopefully you'll be the next example and you'll come back on the show to talk about it. But agree, 10,000% with everything you said about Europe. It is a shame because talent there, agreed as well, is pretty decent or excellent, but that's it. Everything else moves slowly. And then Rohan, I was listening to your answer and you say people just want to meet with you because you're nice. And then I was thinking sometimes they'll even throw money at you, right? They meet with you to help you. They're nice, but then you walk away with 100K. Who knows?
Exactly.
That never happens in Europe. Yeah. Okay. Moving on to sort of YC's involvement in deep tech. That's a topic that's quite famous with YC itself. Everyone's asking, what's the YC of deep tech? And then Gary keeps saying, YC is the YC of deep tech.
Yep.
So talk to me, how's your YC experience with 95% of people building software, and Lou, you not only building deep tech and hardware, but also what we could call a moonshot, where you're not going to get commercial traction in 30 days, right? You're not going to build a machine in 30 days. So how was your experience at YC knowing all of that?
Yeah, I've seen. I'm very familiar with the discourse around what is the accelerator for hard tech and hardware. And personally, I agree with Gary that it is YC today. Whether you're building software or hardware doesn't really matter. YC is at the top of accelerators. And for us, what that really looked like, I think, especially in our batch, there was a 85%, 15% split between, you know, pure software and then hardware, or software with a
That's not too
hardware
bad.
focus.
Hmm.
Exactly.
Yeah.
I think that's actually higher than you might expect. And that was almost done intentionally, where YC wanted to curate a batch with slightly more hardware companies. And if we get into the practicalities of how that plays out, during the batch, you have, you know, group office hours. So you have office hours with your group partner just as an individual company, but then you have group office hours with companies that are building similar product to you or in the same space as you. And that
Hmm.
worked out really well for our batch, because our group office hours were predominantly hardware companies, or again, software with a hardware focus. And so what that meant is that we all adopted this mentality of, how can we build a hardware company? How can we build, in, you know, in our case, a moonshot with the velocity of a software company? And it was great to see how different companies in our group office hours would achieve these things that you'd think are impossible at such a velocity, like, you know, getting LOIs, and not just any small number of LOIs, but LOIs with a value in the hundreds of millions of dollars over, you know, a couple week time span. It really opens your eyes to what is possible, who you can speak to in such a small time frame. And I think that was one of the most valuable things that I got from doing YC, just being surrounded by these other hardware companies that, you know, since the batch has ended, we've still all kept in touch. We've still all carried on that group office hour culture, so we can push each
Yeah.
other to really move as fast as possible.
Yeah. And if I had to say, our partners, it was Aaron Epstein, we had Gary Tan, Michael Siebel, Harsh. While, these are great people on their own, a lot of the advice was just go out and figure it out yourself. And it put a
That's
lot
YC
more,
style. Yeah.
yeah, it's just, there is no secret sauce to YC. What you hear inside the batch and what you hear online and, through all these social medias and whatnot, it's pretty much the same advice. So what, for us, what we realized really quickly is like, oh, well, there is really no shortcut to this. That's still, we have to go out and do all this stuff much faster than we were thinking before. And yes, we'll have the support of our group partner telling us, keep going, but at the end of the day, no one's going to go out and do it for us. So it was really great to have that other group of hardware companies, because someone could try a new strategy that worked. Then we could all go get together and be like, okay, how can we apply that to what we're doing? Or, oh, someone over at SpaceX. We would love to talk to someone over at SpaceX. And really having that community of like-minded people who are building also moonshots in some way really helped us move a whole lot quicker. And again, moving at the velocity of a software startup is key in this space, because that's the benchmark every investor is measuring you up against. Because at the end of the day, you could be a very big company in the hardware space, but if a software company can get there a lot quicker than you can doing, something else, I would rather put my money in the software company than a hardware company that'll take 50 years to get there. So having that mentality, getting it done, is what's important. And at least to me, this batch, because I've been following a couple of batches, but this batch to me felt like winter 2016, which, if you know winter 2016, it was a legendary batch for a lot of hardware companies. That's where Astronis came out of, Relativity, and Boom. Some of the hardware teams in our batch, just insane, next level. I'm really excited to see what the next 10 years will look like, and if people will compare our batch to be the new winter 16 batch.
Let's hope for that. Anyway, yes, there were a lot of very impressive hardware companies in your batch. It's interesting that you kept in touch. Actually, I spoke to someone from the new batch, and I mentioned you guys because we know each other, and they're like, "Oh yeah, we know the guys at Inversion. We kept in touch. That's so cool." So apparently you're in touch with a whole lot of people at YC. And by the way, I wanted to mention as well, sort of double down or repeat what you said, Daniel, that a lot of people think there's some secret inside of
Mhm.
YC. And I used to believe that, to be honest. I used to believe that a few years back when I was really an outsider, didn't know the YC world and ecosystem. I was like, what secrets are kept in there? What's fascinating and what I realized a while back is that what you see on the outside is what you get on the inside. It's pretty much the same.
Mhm.
So just wanted to
Yep.
repeat that because it's pretty
Yep.
counterintuitive and pretty insane. Moving on to yet another topic. I have so many great things and we have so little time left, but I wanted to talk to you about AI and chips. Everybody's passionate about the needs to reshore chips in the US, the implications
Mhm.
for AI.
Mhm.
Everyone realizes that we're going to need advanced chips, and it's far better if they're made and manufactured, created in the US rather than in Taiwan with a machine from Netherlands, right? And so I want to ask you sort of because you're insiders from this world, what's hidden infrastructure, hidden layers that people haven't seen yet, that people haven't built? What's missing, of course, on top of the US version of ASML that you guys are building, but what else is missing?
Yeah.
So go for it,
Uh,
Daniel.
okay, cool. I gave a presentation over in Washington, D.C. a couple of weeks ago talking about exactly this.
Wow.
The back, I'd say early 90s, early 2000s, the US poured in billions of dollars into research to make ASML's machines work. There were two big labs that were working on this problem. It was Lawrence Livermore National Lab and Lawrence Berkeley National Lab, so the lab we're working with, and a consortium of a bunch of companies like Intel was the biggest one. And they poured in $4 billion to make the system all work. And it ended up working. But in the early 2000s, what, the administration then, the Bush administration then did was they let that technology, after all that investment, go out to the Netherlands, and have the Dutch be the ones to develop this machine, just because we didn't really want to do that here in the United States. We had the belief that chips would be so commoditized that the new and real value was companies out of like Google, Facebook, Palantir, who were writing software.
Which
No
is both
one,
true and false at the same time.
both true and false. No one expected software to catch up to hardware so quickly, to the point where now the most, apart from oil, the most valuable resource is who can build the most advanced chips. So if we take a look back, it is pretty ironic that while the US developed advanced EUV lithography, pretty much developed the entire history of lithography, the one capability out of the entire supply chain, or the manufacturing supply chain for semiconductors, the one thing we are missing is lithography. We have great expertise in other areas, or have key partners we can easily get tools from, like Japanese or other countries around the world. But the one thing that is really hard for us to do is lithography. Um, which is, it was a happy coincidence, because this is something we found out, in the later life of what we were building. It just turned out, oh wow, there's this massive hole that no one's built anything in, because the assumption was this is too hard to do, it's too expensive, and the Dutch are the only ones that can do it. And if we take a look towards the next 10 years, not much is changing about the ASML machine. It's all you're getting out of it is more light. They're going to try to, pattern in different directions and different methods to try to get more features out of it, but there will be an eventual wall in which we can't go smaller just due to the capabilities of the machine, and something new will be needed. So, what we asked ourselves is, where do we want that to occur? Do we want, the next 20 years of advanced semiconductors to happen again outside of the US without no control? Or would we rather be the masters of our own destiny and really sit down and do the hard work to build advanced semiconductor tooling here in the US, not only from the lithography side of things, but the entire tech stack. Really flip it on its head and ask ourselves, is this the best way we should be doing things? Could we do things in a different way? And as we reach the end of the usefulness of CMOS, new advanced structures will become a whole lot more useful, like quantum, like photonics, more 3D structures at the actual wafer level, architectures that we can't even imagine today. We need the tools to be able to build the future. We don't have that capability today as humanity. Yeah.
I think it's worth exploring a little bit of context about why is it that us building a novel kind of lithography machine is going to unlock so much more performance gains and so many more things in the semis industry that we don't have today. If you look at, as Daniel referred to CMOS, for anyone who doesn't know what CMOS is, it refers to today's traditional chip architecture, the kind of electronics that we are using to build our chips, and is based on traditional silicon. So if you want better performance with these traditional chips, you can really do three things. If you think the transistor is this fundamental unit of power of a chip, you can increase how many transistors you have in a given area on your chip, increase the transistor density. You can change what kind of transistor you use. And so we see this trend where actually transistor architecture itself has become more three-dimensional over the past couple of decades, because it turns out it gives us the ability to run these transistors much faster and have much better control over these transistors. And so then the third thing you could do is actually you forget about the conventional architecture and you look to a new kind of architecture. So it could be quantum based, could be photonics, it could be something else. And we actually see that we're able to target all three of these areas with the lithography machine that we're building. In the case of shrinking the wavelength of light that we use to do lithography, there is a direct unlock in increasing transistor density. If we can increase the power of the light that reaches the wafer, then what that allows us to do is manufacture more a high aspect ratio feature, more three-dimensional features on the chip that applies to both the next generation of transistors, but also these emerging architectures. What do we need to build waveguides with photonics? What do we need to trap electrons with quantum? And there's unlocks across the board with litho. If we look beyond litho, a couple other interesting paradigms in semis at the moment. One of those is advanced packaging. So that's almost like a cheat code way of continuing Moore's law. So Moore's law, very broadly, is how do we increase the transistor density? How do we pack in more transistors to a given area? Advanced packaging allows us to, rather than building one chip where we put everything onto that one chip, we can split that up into multiple different chips and package them together in a way that it's almost acting as one chip. So that one chip is the holy grail, but the second best thing is do better packaging. And then when you look at emerging architectures like quantum and photonics, something that I think you asked about, missing infrastructure layers. Something I think is really important to see more development with is what we call the PDK. So it's a process design kit or process development kit. That is the set of rules that tells us what can we manufacture with a given set of machines. And the way that PDKs are standardized with traditional chips put together by companies like TSMC and Intel and Samsung, we don't see that level of detail for PDKs with quantum chips and photonics chips. And that is a lot of work that needs to be done. There's a company from a couple of batches ago, Conductor Quantum. Their focus is actually on the software layer around quantum
Remember
chips. I
them.
think they're doing some very important work there, which more attention needs to be paid to.
Yeah,
Very
we
cool.
should.
Thanks for the shout out.
Yeah,
Sorry,
we
go
should
ahead.
just think, no longer living in Moore's world. We need to start thinking about what does a post-Moore world look like. Moore's law will die, at one point, whether it be next year or in a couple of years, but it will die. We need to start preparing a lot of the infrastructure to realize what does, compute look like in a post-Moore world.
It's interesting because people have been predicting the death of Moore's law for 35 years and it's still here. Thanks to,
Yep.
stuff like you guys. You're the reason maybe it doesn't die for another 20 years, hopefully. So let's see. Okay, I do have to let you both go pretty soon. I would love to have this, we need to, next one we'll just schedule 3 hours. So,
Yeah,
because
we
we have
could
so many
talk for days.
cool things. Quick sort of rapid fire question. Just, one last quick question. I want to hear you both. What's the craziest, but in your mind, most likely prediction about chips or chip making for the next 10 years?
Okay, for me, I think it's actually, we will see, especially, I'm very bullish on photonics. We will see photonic chips in consumer products. What we see today is that companies are starting to build photonic chips, but really the application is things like data centers, far away from the consumer. What I mean is that we're going to soon see, within that time frame of a decade, your phone is going to run using photonic chips, and it will speed up the rate at which we can do calculations, the rate at which data moves around, just give a great user experience, enable things like better edge AI running on small portable devices. That's something I'm really excited about. I think that is coming in the next decade.
Very
Yeah.
cool. Daniel, you have
If I had
something?
to say, I'd say usable quantum computers, specifically for applications
Wow.
within AI. I think within 10 years, especially with the work that IBM is doing, we are more likely than not, like 90% likely to see a GPU analog quantum computer, something that is
Wow.
training AI models. And what that really, if you can have a quantum computer unlock a lot of the training that, current architectures can't realize. We'd be able to see probably the next paradigm of AI once that is possible.
Impressive. All right, you guys, thank you so much. That's the end of the show. I have to let you go. Where can listeners follow you? Just get in touch or follow what you guys are building.
For now, jump onto our website, inversionsemi.com. Reach out to us. We'd love to chat with you if you're interested in what we're building. We're also hiring at the moment. And so if the mission excites you as much as it excites us, then we want to speak to you. Otherwise, just look out for what we put out on the internet. There'll be a lot more of that coming.
Yeah. Follow
Very,
us
very
on
cool.
Twitter as well. Yeah.
Go follow Inversion Semi on Twitter. Guys, thank you so much for taking the time. I had a blast.
Thank you for having us on. Really appreciate it.
All right.
And good
Take care.
to chat again. Good to catch up.
Awesome. And to our listeners, if you're still here, thanks for watching until the end. Please don't forget to subscribe, rate us on your favorite podcast app. If you're on YouTube, even better, you can watch us. Subscribe on YouTube as well. And I'll catch you on a next episode of the Lobster Talks. Bye, everyone.